So we are discussing the elements of band theory of solids, and in the successive classes we have already understood the basic elements of band theory and how they arise uh, in the context of the solid physics. So, brief recap of what we understand about the structure or the periodicity of the solids are, as you all know, that atoms and groups of atoms, when brought into close contact, stick together because of the chemical binding, sorry. The resulting stable spatial configuration is governed by electrostatics due to the charge diodes, okay, and the quantum mechanics for the electrons. Under given thermodynamic conditions, it represents the state of condensed matter with the lowest total energy, the ground state. For molecules consisting of a small number of atoms, the variety in structure and molecules consisting of a small number of atoms, uh, the structure, the functionality results from the many possible combinations of different atoms from the periodic table. A larger number of identical atoms or identical groups of a small number of atoms can form a cluster or macromolecule with identical building blocks, that is uh, conventionally we known as the polymer chains. With an increasing number of identical building blocks, a number of atoms, these eventually results in macroscopic structures whose physical properties are determined by the chemical nature of the constituents and their configuration in space. So these macroscopic structures are understood in a more restricted sense as condensed matter, apart from solid state physics, which comprises matter in the liquid or solid phase. So crystalline structures result from a space-filling periodic repetition of the same building blocks, an atom and its nearest and next nearest neighbors. So these configurations are characterized by a long range order, which causes sharp Bragg peaks in diffraction experiments. These Bragg peaks are used to identify crystalline solids or solids in the crystalline state by their crystal classes. So as we have already gone through this crystallinity and the crystalline solids in the preceding chapters where we discussed the structures of solids, and crystalline solids will be the primary subject of uh, our discussion. Some elementary concepts for describing their structure shall be modified in time to time in our due course. And before discussing the crystalline structures in more detail, we should mention other forms of condensed matter, namely the quasi crystals, the amorphous solids, liquid crystals, and soft matter. So quasi crystals exhibit long range order, but they are not simple periodic structures. Instead, they result from superimposed incommensurate periodic periodicities and are self similar. So examples are one-dimensional Fibonacci chain, or the Penrose tiling. Uh, Penrose tiling allows a local five-fold symmetry, which is prohibited in crystalline solids. In contrast, this long-range order is missing completely in amorphous solids, which are characterized by disorder in the spatial configuration of the structural disorder. The X-ray diffraction patterns of quasi-crystals show sharp peaks owing to the long-range order, while those of amorphous solids are diffuse. Liquid crystals have long-range order, but are not at all spatial directions. The building blocks, usually large rod-like or cyclic molecules, are arranged such that a long-range order exists with respect to the orientation of these molecules in at least one direction, whereas in other directions, a liquid structure prevails. because of their order disorder phase transitions at room temperature, which can be triggered by applied voltages. Liquid crystals have seen widespread use in displays and large-scale television screens. Finally, we refer to soft matter, a class of materials that comprises foams, polymer melts, biological membranes, and colloidal systems. Their particular material properties result from structuring on a mesoscopic scale on which normal liquids and solids are homogeneous. So let us restrict or return to our basic problem of the periodic structures, and their symmetric description can be found in the beginning of the most solid state physics books and shall be repeated briefly. An infinite periodic structure can be characterized by a point lattice which in three dimensions is defined by the set of lattice vectors, that is Rn is equals to n1 a1 plus n2 a2 plus n3 a3 with linearity or linearly independent vectors ai, where I runs from 1 to 3 in this case, the primitive lattice vectors, and integers ni, where I runs from 1 to 3 again combined to n, that is n1 n2 n3. Point lattices in 1 and 2 dimensions are defined analogically. While in one dimension, there is only one point lattice, and there are 5 in 2 and 14 in 3 dimensions. So uh, now let's discuss about the solid as a many particle problem. What we understood the solid as being comprised of ions. Ions mean either nuclei and the closed electron shells and valence electrons. A more rigorous approach would start from nuclei and electrons, but simple consideration of the spatial extension of electrons in different shells of the isolated atoms show immediately that this is not necessary. The wave functions of electrons in inner shells, which we conventionally call the core electrons, with binding energies of hundreds of thousands of electron volt, extend over a distance much smaller than the lattice spacing of a solid. And in fact, uh, you can see this from, one second, from this figure. In fact, when the atoms are assembled into the configuration of a crystal lattice or likewise of a molecule, cluster, liquid, it will be the outermost weakly bound valence electrons which first experience the presence of their nearest neighbors. So they will rearrange from their states in the isolated atoms into those which establish the chemical binding. Together with the electrostatic energy of the ion configuration, this defines the stable structure, right? So, uh, for studying the solid as a many particle problem, our basic intention is to write the basic Hamiltonian, which defines the solid as a quantum mechanical many body problem. The effectiveness of chemical binding depends on the overlap of the electronic wave functions at neighboring lattice sites and on their coordination number. Thus, metals prefer a closed packed structure, namely the body-centered cubic BCC and FCC face-centered cubic lattices, with localized electrons acting as glue between the positively charged ions, such as metallic binding, while in binary ionic crystals, electrons are transferred from the cation to the anion to complete their outer shells, or ionic or heteropolar binding, and form lattices dominated by the electrostatic interaction, like the rock salt structure. Rare gases with closed shell configurations as well as larger molecules form crystalline solids due to the weak van der Waals forces and are stable only at low temperatures. So elements of fourth group of the periodic table generally share each of their four valence electrons with the four nearest neighbors. So in directed covalent bonds where covalent or homopolar binding, which results in the diamond structure, a mixture of the covalent and ionic binding, thereby the contribution of the latter increases with the polarity of the material in typical for the zinc blend structure. A dominant covalent binding is typical for semiconductors. So in most cases, the distinction between valence and the closed shell electrons is justified by the large energy separation, which can be detected by the photoelectron spectroscopy, we call it PES, with reference to the heavier elements, including transition metals or the rare earths and their compounds, for which D states are in the same energy range as the S-like valence electrons. One should keep in mind, however, that even complete D shells can participate in the chemical binding, the influence the electronic structure, right? So let us write the Hamiltonian of the solid. So here you can see the Hamiltonian of the solid. Uh, is the composition of a solid out of valence electrons and ions justify writing the Hamiltonian like that? Let us take the spotlight here for your better understanding. So here it is that H0 is nothing but H Hamiltonian for ion, Hamiltonian for electron, and Hamiltonian for electron-ion interaction. So the first term depends only on the coordinates of the ions and reads H ion is nothing but summation I is equals to 1 to N1 pi square divided by twice Mi plus half summation I comma j equals to 1 to NL, where I not equals to j, V is the potential term Ri minus Rj, where Pi, Ri, and Mi denote the momentum, position, and mass of the ith ion respectively. And Ni is the number of ions in the crystal volume Vc, where V Ri minus Rj can be a quite general ion-ion interaction potential, but for point-like ions with charge Qi is equals to the sign of Qi Zi and positive integer Zi, it will be the Coulomb interaction such as Vri minus Rj is equals to Qi Qj divided by 4 pi epsilon naught modulus Ri minus Rj. Here epsilon naught is the vacuum dielectric constant. The assumption of point-like ions is justified for closed shells with tightly bound electrons. This situation is visualized as in the case of this figure. So these are the for valence electrons, these are the core electrons, these are the ions, and these are the lattice constant. Here the plotted as R versus periodic potentials and wave functions of core and valence electrons shown respectively and their respective energy levels. Excuse me. The electron part of H0 is given by this HEL is nothing but summation IL is equals to 1 to NE PL square divided by twice M plus half K comma L is equals to 1 to NE E square divided by 4 pi epsilon naught RL minus RK, where PL and RL are the momentum and position of the nth electron, M is the free electron mass, and capital Ne is the number of electrons in the crystal volume. The charge neutrality of the solid requires that summation I is equals to 1 to NL Qi minus E times Ne is equals to 0, and the interaction between electrons and ions is described by H electron ion is equals to summation L equals to 1 to Ne summation I is equals to 1 to NL. V is a function of RL minus RI, which approximates at summation L is equals to 1 to NE, I is equals to 1 to NL, Qi times E divided by 4 pi epsilon naught RL minus RI, where the last expression is the approximation for point-like ions. So far, the spin of electrons or ions did not appear because neither the kinetic energy nor the Coulomb interaction depends on spin. The expression for the kinetic energy is that of the non-relativistic formulation. In principle, one could have started for the electrons from the relativistic Dirac operator, which is in fact used in band structure theory and becomes relevant for solids composed of atoms with large Zi. However, in most cases, it is sufficient to consider just the spin orbit coupling in the electron part of the Hamiltonian, such as SO for the spin orbit, that is the Hamiltonian for spin orbit coupling is h cut divided by 4 m square c square summation over L grad L V effective RL cross PL dot sigma L, where V effective RL is the effective single particle potential which will be introduced later, and sigma L is the vector of the Pauli spin matrices of the LF electron. A similar term can be added to the ion part of the Hamiltonian in order to account for the nuclear spins if their influence is addressed. But even without spin orbit coupling, the spin becomes important in the presence of a magnetic field when the Zeeman term So, when the Zeeman term causes removal of spin degeneracy, and because of the fermion character of the electrons by considering the Pauli principle when dealing with the many particle aspect of the problem, moreover, spin alignment and spin excitation are essential for magnetic properties. So to start with the elements of band theory, we have to consider the energy band formation. And so far, we have completely neglected the effects of the ion cores on the motion of the valence electrons, right? I repeat, we have completely neglected the effects of the ion cores on the motion of the valence electrons. We consider valence electrons to be those outside of a closed shell configuration, so that number one is sodium has a single 3s valence electron outside a neon core. Magnesium has two 3s electrons outside a neon core, and gallium has 10 3d electrons, two 4s electrons, and one 3p electrons outside an argon core. The s and p electrons are usually considered as the valence electrons since they are responsible for bonding. Sometimes the mixing of d electron atomic states with valence electron states is important. So to get some idea about the potential due to the ion cores, let's consider the simple case of a isolated sodium plus ion. The ion has charge plus E and attracts an electron via the Coulomb potential, like Vr is equals to minus E square upon R, where if R is greater than obviously the ionic radius. For a pair of sodium ions separated by a large distance, each conduction electron, that is 3s electron in sodium, has a well-defined atomic energy level. As the two atoms are brought close together, the atomic potential, that is Vr, begin to overlap. Then each electron can feel the potential of both ions. These gives rise a splitting of the degeneracy of atomic levels. I repeat, for a pair of sodium ions separated by a large distance, each conduction electron, that is the 3s electron in sodium, has a well-defined atomic energy level. As the two atoms are brought close together, the potential, the atomic potential VR begin to overlap, then each electron can feel the potential of both ions. These gives rise to splitting of the degeneracy of atomic levels. For a large number of atoms, the same effect occurs. Think of a crystal structure with a nearest neighbor separation of 1 centimeter. The energy levels of the system will be atomic in character. However, as we decrease the nearest neighbor separation, the atomic energy levels will begin to broaden into bands, as shown in this figure. The equilibrium separation of the crystal is the position at which the total energy of the system is a minimum. In all crystalline solids, the electronic energies form bands of allowed energy values separated by energy gap. This is the energy gap, which called the bands of forbidden energy values. These energy bands determine the electrical properties of the solid, whether it is metal or semiconductor or insulator. So this is a typical Coulomb potential like behavior. Here varies as 1 upon R. These are the bound states, and these are the band formation for atomic levels. Previously, it was like a single straight line, which is atomic levels, and as it comes closer, these bands splits into bands like that. So this is the important consequence of the uh, when electron feels the potential due to two nearest neighbor ion pairs, as seen in this figure. So let us discuss what happens for the periodic potentials for the case of translation operator. Because the crystalline potential seen by a single electron in a solid is a periodic function of position with the period of the lattice, it is useful to introduce a translation operator T, defined as T operating upon fx gives me fx plus a, where fx is an arbitrary function of position and a is the period of the lattice. So it is clear that T, this T operator, the translation operator, commutes with the single particle Hamiltonian of the form minus h square by 2m del 2 del x2 plus vx. Because if we let x prime is equals to x plus a, we can see that del x prime is equals to del x and vx prime is equals to vx. So one of the most useful theorems of linear algebra for the study of quantum system states that if two operators commute, one can find common eigenfunctions for them. That is, they can both be diagonal in the same representation. Let psi be the eigenfunction of h and that of translation operator t. That is, h psi is equals to e psi and t psi is equals to lambda psi, where e and lambda are eigenvalues. Clearly applying t to psi n times gives t to the power n upon psi x is equals to lambda to the power n psi x, which is psi x plus na. If we apply periodic boundary conditions with period n, then simply psi x plus na is equals to psi x, and this implies t to the power n operating on psi x gives the same eigenfunction psi x, so that my lambda to the power n is simply 1. Thus, lambda to the power, if lambda to the power n is equals to 1, thus lambda itself must be the nth root of unity, that is e to the power I 2 pi by n times small n, where small n takes the values of 0 plus minus 1, and we can write lambda as lambda is equals to e to the power I ka, where k is equals to simply 2 pi by na times n, and then it is apparent that two values of k which differ by 2 pi by a times an integer give identical values of lambda. As usual, we choose the n independent values of k to lie in the range minus pi by a less than k less than equals to pi by a, the first Bilua zone of a one-dimensional crystal. For more than one dimension, this TR, which is the translation operator, translates to a lattice vector R. That is TR operating on psi R is equals to e to the power I k dot R psi R, where k is equals to simply 2 pi by n, n1 b1 plus n2 b2 plus n3 b3, where n1, n2, n3 are integers and b1, b2, b3 are primitive translations of the reciprocal lattice. We have assumed a period n for periodic boundary condition with L1 is equals to Na1, L2 is equals to Na2, and L3 is equals to Na3. And values of N1, N2, N3 are chosen to restrict K to the first period. So these translation operators plays an important role in Bloch's theorem. And Bloch's theorem eventually plays a very vital role in calculation of energy bands. We have already came across the chronic penny model, the free electron theory, the nearly free electron theory in the successive classes of the introduction of the band theory of solids and the free electron dispersion. Now a bit about the electrons in a periodic potential, and we will discuss the solution of a general wave equation for electrons in a periodic potential. The solution is investigated particularly at the zone boundary, and the potential U is periodic with lattice, that is UR is equals to UR plus R, that I already written in the first class of the band theory of solids, that the potential is periodic with the periodicity of the lattice, that is the R is the vector of the direct lattice, and it can be represented as a Fourier series with the reciprocal lattice vectors. That is, UR can be written as summation upon G, summation over G, UG exponential e to the power IG dot R. Since U is a real function and U minus G is equals to UG star, the deeper reason for the success of such an approach is that for typical crystal potentials, the Fourier coefficients decrease rapidly with increasing G. That is, for the unscreened Coulomb potential, that is UG proportional to 1 upon G square, the wave function is expressed as a Fourier series or integral over all allowed Bloch wave vectors K. That is, psi r is equal to summation upon K Ck exponential I K dot R. The kinetic and potential energy terms in the Schrodinger equation are grad square psi is equals to minus k square Ck exponential I K R, and U psi is equals to summation upon G and summation upon K UG Ck exponential I G plus K R, with K prime is equals to K plus G and can be rewritten as U psi is equals to summation upon G and summation upon K prime UGC UG. Sorry, this is not U, this is C instead. It's my mistake. It is not U. Instead, it is C. C K prime minus G exponential I K prime R. Now the Schrodinger equation can be rewritten as an infinite system of algebraic equations like lambda k minus E Ck plus summation upon G, over G UG Ck minus G is equals to 0, with lambda k is equals to h car square k square by twice m. So let us discuss about the approximate solution at the zone boundary. We assume that the potential energy has only one important Fourier coefficient U for the shortest reciprocal lattice vector G. Also, we have U minus G is equals to UG. Thus, the one-dimensional potential has the form Ux is equals to twice U cosine Gx, and we consider the solution at the zone boundary, that is the vicinity of k is equals to G by 2, right? The kinetic energy is then the same for K is equals to plus minus G over 2. That is lambda K is equals to lambda K minus G, which is h cut square by twice m G square divided by 4. And Cg by 2 is an important coefficient of the wave function. The C minus G by 2 will also be important. We will now limit the k vectors for the series of previous equation psi r. This one psi r is equal to summation upon k ck exponential I k r, right? Uh, to just 2, and for the coefficient vector, this one c g by 2 and c minus g by 2, these matrix or this vector coefficient vector, and the determinant is lambda minus e u, the off diagonal elements, lambda minus e, that is lambda minus e whole thing square minus u square is equals to 0. So if we plot these periodic potentials, we can see uh, this type of behavior. And this line is for potential. This is minus a, this is 0, this is a, and the red one is psi minus square, and the blue one is psi plus square. We have plotted the periodic potential U in one-dimensional cosine solid lines, and the squares of the potential psi plus and psi minus for the vector at the zone boundary k is equals to g by 2, that is pi by a, that is the boundary of the first Brillouin zone. With lambda is equals to lambda k, which is also lambda minus k, which is the value of h cut square by twice m g square by 4 for k is equals to simple g by 2. Thus the energy values are E plus minus is equals to lambda plus minus u, which is lambda h cut square by twice m g square divided by 4 plus minus u. At the zone boundary, a splitting of the size E plus minus E minus is equals to twice u occurs. The center of the energy gap is given by the energy lambda k of the free electron dispersion. The ratio of the coefficient c g by 2 divided by c g by 2 divided by c minus g by 2 is equals to minus plus 1. The minus solution of the lower energy standing cosine wave, cosine standing, and plus solution, that is psi plus, is a standing sine wave, sine standing. So for the lower energy, the binding, the state of electrons are localized at the potential minima, that is at the atoms. For the upper state anti-binding, the electrons are localized between the atoms. So both wave functions have the same periodicity since they belong to the same wave vector k is equals to g by 2. We note that the periodicity of psi is 2a, while the periodicity psi square is equal to the lattice constant a.